Hello, in this video I'm going to go over my latest game for the Game Boy, which is called PlantBlitz. It is based on the code for the Master System version of Sonic Blitz. The difference is we don't have buildings this time, we have a load of carnivorous plants who are trying to devour everything. So your job is to cut them back with your trusty plane. So first off with, I will boot up the ROM for you to see. So we have our trusty guy here, Marco, and then we have the carnivorous plants. So the plants themselves, these common plants, they all take one hit to kill. Sorry, that's 2 hits for them. The white one takes 1 hit. So you can push right to accelerate to go faster to clear the screen, and you can go down, which allows you to fire bombs faster. So there are 10 levels, and each level gets faster and faster, and the plants grow higher and higher. So be sure to check out the game from the link to the video. Now I'm going to get into the source code, which I will provide for a version of this called OpenBlitz. First off, I will show you the differences. So I will provide the source code for OpenBlitz. So this one has a more basic feel. The idea is that you use the source code to learn from and then maybe upgrade various graphics to use your own. So other than the only the change of graphics is the difference. As you can see, the game plays totally the same. So the key things with this version that I would like to go over are the collisions and the sound effects. Lots of the other things I've already covered in previous videos. I have tidied up a few bits and pieces to make this easier to code, but most of the things here are pretty much covered in the other videos that I've done on the Game Boy. Some exemptions might be the double height printing commands here. There's an 8x16 font in here, as well as the standard font set, which I usually use. All the graphics is in here. As per usual, I have the defines here, which organise where all the graphics will be. So let's jump into some of the more interesting things about this version here. So first off, to create the plants and to have the shape of the plants, I use different arrays here. So this array here details the head type. So we have, if I just open up the graphics a minute for the plant types here, this will make everything a lot clearer when I'm talking about it. I will provide the sprite sheets as well to OpenBlitz and the tile set as well. So these are the plant heads and parts here. I'll just change this a minute so we get past. So this is the standard Game Boy palette here. And then you'll see that there's 3 types of plants. There's the ones facing to the right, and then there's these facing to the left, and then there's a dead head for each of them once they die. So this is there's your 3 types of plants there. So at the start, plant 2 is the is this plant type here, plant 1 is this one, and plant 3 is this one. So there are 9 of these. Going across the screen here. So these arrays here are just to set which types there are. As the game goes on, you get more and more of the middle type. The reason for that was I was thinking about having them fire some sort of projectile at the player, but then I kind of thought it would potentially change the game too much, so I decided against doing that. But the idea was there anyway, and over time they would all become the sort of projectile firing type. But this does give you hopefully some ideas on what you could do to maybe change some types of enemies on some of your games. And then this thing here is an array of heights for the plants. The plants are made from 16 by 16 pixel images, so that's 2 by 2 tiles. So these here are the heights for them, and then I set out the maximum height being 13. I got that by just creating a virtual sort of level here. So if you, some of the things you can do to kind of design levels on the Game Boy is create like a grid, a pixel grid here, and then just get some colours and fill that in. Now you can think of this grid here as being a virtual tile map for the actual screen. So for our example here, we can say that's the floor there, and then each vine is made of parts like this here. So each vine graphic is 4 of these. So now if we stack these up, we can get a feel for how many we should maybe have. So on the top here we know that we've got the heads up display there, and our player in this game is 16 by 16 as well, so they will be that. And then we kind of want some space to be able to drop a bomb and maybe for it to move one tile over or down. So this is kind of how I came up with the sort of height there. It wasn't just height sort of plucked out of the air. I did kind of play around with different heights and then drawing out the pyramid shapes in here as well to kind of see what works. Now in the level manager, although there's static and dynamic there, oh yeah, well, some of the things that I kind of did to animate the plants was to just use tile streaming. I believe that's what I did. Yeah, here we go. So as in the tile streaming video which I did previous, these different parts are in the plant manager where we update the frames of the plants just by copying the tile data over the existing frames so that it allows to animate them easily. And then there is setup here for potentially having bullets, but I obviously didn't add them in. And then the kind of interesting thing about the plants is they have a number of different collision things associated with them. Each plant has a collision map, which is a kind of unique thing to this. So by using the collision map, it means I didn't have to have, or rather using a collision map for each plant meant I didn't have to have a collision map for the whole screen. And the numbers which you put in the collision map are not related to anything other than just indicating whether that tile location is clear or whether there is something there. And the plant heads themselves have lives associated with them. So this is the structure that contains the plant. The bombs and the player are made of sprites on this game, so the sprites obviously don't totally align with the tiles on the tile map, so you have to adjust the position of the sprite and then divide its location by 8 so that it aligns to a tile on the tile map, and then we can then check to see whether it's hit one of the tiles in the collision map. But what we also add is a collision rectangle around the plant, so we don't bother checking to see whether we've hit a tile in the collision map unless the location of the bomb or the character is inside the collision rectangle of the plant. So this just limits the amount of work that we need to do with checking tiles and things. And then some of these here are constants to use with the collision maps here. So you'll see we've got the maximum size of a collision map. So how we get that is that's the maximum height that the plants can be. So we need twice that because the plants are 2 tiles in width. So when we draw the plant initially, all we do is every time we plot a tile on the screen, we allocate a tile in the collision map. But as the physical screen tile location is not going to be the same as the collision map, we need to subtract this number. Where are we? Sorry, this number here, we subtract 5 from it. As the plants, the highest, or rather the lowest they can start on the screen is at tile 5. So when we come to plot a plant, if we subtract 5 from the tile's Y position, then it will relate to the collision map's Y position. Hopefully that will make sense. So when we, well, first off, so here's the public function here for check for collisions. So these 2 values we pass in to check for collisions. These are actually pixels of a sprite. So what we first need to do is remove the offsets that the sprite location would have. So to translate a sprite to the physical screen, you add 8 to its horizontal position and 16 to its vertical position. So as we need to do the reverse, we need to subtract 8 from the sprite's X position and 16 from its Y position. That will then give us which tile it's over the top of on the actual screen. And then to iterate over our array of plants, we have a private struct pointer here. This is our array of plant structures. So anything with a Z in front of it is my way of designating that variable as being a private variable. Obviously there are no real sort of private variables in C, but I usually put a Z there so that I don't pick these variables up outside of the structures. So if I carry on with the collision routine here, so then what we do is we use a mask variable or number over the top of the X position here. By masking the number with 248, we're making sure that any of the last 7 bits, or rather any of the last 3 bits, are removed. So what this will actually do, if I show you it here, so if we put in the hexadecimal number F8, you'll see these are the bits which are set here. So these numbers at the end, the bits which are clear, they can be a number between 0 and 7. So what we're doing is we're taking those away. So the tile location will always be aligned to 8 pixels here, using this mask to clear the bottom 3 bits. It's a quick and easy way to align things to 8 pixel sets. Then what we do is divide the bullet or the objects X and Y positions by 8 by using a bit shift operator. Now what we can do is we can iterate over all of our plants to check to see whether the X and Y here is inside the plant's collision rectangle. So the plant's collision rectangle is purely in tiles as well. But obviously before we check that, we have to make sure that the plant is actually alive. So there's actually a counter in the plant themselves. So every time you draw a tile of that plant, it adds 1 to the tile counter. So we then know how many parts there are of that plant. So when that tile count reaches 0, then we know that the plant is dead. So we can then set the boolean here to false to indicate that it's dead, and then we no longer need to check to see whether there's a collision at all here. We can skip that then. So if the point bx and by is inside the collision rect, then we carry out our second collision detection function here, which is the private function hitPlant. So what this takes is the ID of the plant. So as there are 9 plants, that can be 0 to 8. And the tile location there. So if we go up here, so what we need to do now is translate this position here to that of the collision map. We do a bit of error checking here, although most of these error checks can probably be removed once the game has been tested and debugged, as they do take clock cycles of the Game Boy. As the game isn't too strenuous on the Game Boy, there's no real reason to remove these, but if you were kind of struggling after you completed a game due to it running too slow, then these could be things to think about afterwards. So if I split this here, then we can compare the header with the module here. So first off, we use px and py, which are 2 temporary variables, to translate the coordinate here in bx and by to the collision map coordinate. So we need px to be either 0 or 1. So by subtracting the collision rectangle's x coordinate from px, which is assigned this one here, this will then translate it to either 0 or 1. If it's greater than 1, then we throw an error with an error code. I don't know if I've covered this one here, but this is just another function which throws an error but allows you to pass an 8-bit number to it, which can obviously be useful. Debugging is kind of complicated on the Game Boy because the screen is only 20 tiles across, so any error messages you put out kind of are likely to be only understood by yourself, really. Hence the weird text names here. Obviously you could put more detail here, but it's purely for your own benefit, really, what you put here, not for anyone else. So once we get past here, we know that px is either 0 or 1. Then what we need to do is translate the Y position we passed in here. So like I said, the plants can only ever start on the screen from tile location 5. So by subtracting that from PY, PY will only ever now be between 0 and 13. If PY ever equals the maximum number, then we throw another error. Now here what we need to do is, as this collision map array here is one big clump, what it actually is two sort of or rather 13 rows of 2 tiles. So what we do is times py by 2, add px to it, and then that will give us the actual offset into the array here. Then we use this temporary variable here, ctile, to read what byte is in the collision map. So the way that this collision map's done here, obviously in this game I only use it very simply, but on other games you could obviously have various types in your collision maps. For example, if it was like some sort of height array, you could check to see what tile you collided with, and maybe then set something to a specific pixel height. Then what we do here is, if the tile returned is greater than 0, then we go through this other part of code here. Otherwise we return false. So what we first do is, if the head lives are greater than 0, then we subtract 1 from the head lives. Then if the head lives equals 0, play a sound effect for the plant dying, although there's probably no real point for that because it's probably not heard over the explosion, to be honest, but it's there anyway. So if the head lives equals 0, then we need to reuse px and py to get the tile location to draw over the plant's head tiles with the dead head version of itself. So as there's 3 different plant types, we need to draw which head type it is, which is why we've got the plant type variable here. Now on the other side here, if the lives equal 0, then we know that we can start taking away tiles from the plant and reducing its height. So to begin with, we zero out the collision map tile. Then we subtract 1 from the tile count. Then we reuse the passed in bx and by to then plot a tile at that location to clear out the tile on the screen. Then we quickly check to see whether the plant tile count has reached 0. If it has, then we set the plant alive to false. So that's probably all I really want to cover with the plant bit. Some bits to jump into which might be of interest, I suppose, are the creating the new plant part really. But I think that was in the tile streaming video where I actually created the plant. I don't know whether I don't think the collision map code was quite the same there, but as you can see here, each plant head has a lives set to 2 in the new plant part. When we create a plant, we obviously need to clear the tile map, the collision map. And then we use the passed in parts here to assemble the plant. So we draw its head first, and then we use this command here to fill the collision map with a collision tile. All that does is we first calculate where in the collision map we need to be. So this will actually just plot 2 tiles in the collision map, as each collision map is 2 tiles across by 13 down, as I said. This just sets up the head part, and then this then draws the stem part here using a do while loop. And the reason why we kind of do it this way is because we're only creating the collision map in steps of 2 segments across. We have to draw the top 2 tiles of the vine and then the bottom 2 tiles of each vine every other loop through. Again, by all means, definitely go through any of this that you're not sure of and tweak around with these things, which is the whole reason of giving you the source code in the first place. I'll go over some key parts which I think I haven't really sort of touched on or covered before, and then the rest is up to you to do yourself. So the level manager doesn't really do much here. All it does is handles which tile we're using to draw the floor tile. So there's not really much in there. The other key differences here over the Blitz version on the Master System is sound effects. So we can't create the same sort of sound effects. We can create the music the same. The same music track is there. The differences in here now are usually when I create different sound effects, I usually create like a number of different arrays of bytes here, depending on which sound channel you tend to use. So that the 2 main ones are used for sound effects are channel 1, which has the tone sweep and the volume envelope in there. Again, you'll need, if you're not familiar with that, then you'll need to check out the GameBoy sounds video that I did to go through that. And then this one here is just using the noise sound channel there. So if I come back to here and jump in, again, most of these are all the same as in the GameBoy sounds video here. So I use sound channels 2 and 3 in this game. Channel 3 I use to play the music. The weird thing is most of the emulators I've seen, for some reason channel 3 sounds totally alien to how it sounds on the actual Game Boy, so that's something to be aware of. For some reason on these emulators, channel 3 sounds really deep and bassy, whereas when you actually play it on the real machine it's nothing of that. And I use channel 2 just to create beep sounds for the plane's engine. So you'll see here, these enumerations here are just to give the sound effects names. So we've got the plant die sound effect here in voice 1. So this enum starts at ID 1. So I use these here to indicate which sound effect I actually want to play. So as you can see there, the level clear sound effect is this one here. These all use voice 1 or channel 1, if you want to call it that, and then that takes in 5 bytes to actually create a sound there, whereas channel 4 only needs 4 bytes, which is why I decided to split the arrays here, because otherwise we're using more memory. And then the 2 effects here to play a sound effect there. So this makes it nice and easy there. We can say, here we go, play sound effect with voice 1, and then pass it the enumeration ID, and then that then sets everything up for us here. So if I scroll down to where that is here, so here we here, there we go, play voice 1. So we use the lseed variable, which is a kind of a global variable I use over and over again. So as each sound effect in here takes 5 bytes, we need to time that ID by 5 to get to the array location. We then use this global variable p-tile here, which is a const, rather an unsigned byte pointer. Point it at our sound effect array, then load out the data byte at a time, and then pass that byte to the relevant Game Boy register there in sequence to create that sound. So one of the different things here is you notice I didn't cover the first one here. So this is a kind of different thing which I did here. So there are some settings in the Game Boy sounds which have a sound playing constantly. Depending on whether you've got this set to 8.0 or C0. So I leave both of these blank here for doing the sound bomb drop. And the reason for that is I set up a sound start using the height that the player is on the screen. So I pass that in here for the bomb drop, and then we do some tweaking here. First off, we start at location 0 in our sound effect array for voice 1 here. So we take in these, although we only need to take in the first 3. Then what we do is we times the height by 4 using the shift register there. and then to get the desired sound here, I loaded up the GB sound ROM and then found the frequency that I wanted. And then, so if you're not sure what I'm talking about here, in the GBDK folder there is a sound ROM here, and this allows you to quickly go through and test out various sounds and make various sounds and play with them in the emulator. So you can then reproduce them by inputting these bytes here into the relevant registers. So these are the sound registers there for sound channel 1, NR10 to NR14, which is right here, look, NR10 to NR14. And then the 1950 I obviously got by tweaking around with the frequency and settings here. So I could even I can't even show you here. So if we go in here and then match what's in here. So if you look at these here, I will then use this to match these here, and then you'll get an idea of how I reached what I did. Right, now this is now you'll notice that this sound will stay on constantly until you do that. So notice here, which is why to stop that bomb, in fact that shouldn't be there. So these values here I've literally passed into stop the bomb sound effect. We set these up, and then pass in the various bits then into the registers here to create those sounds. Those are the key things I wanted to cover in this video, really. I don't think there's anything too much more to go over. I'll go into more detail in the master system video there, but I don't really need to reference that at all for you to kind of look at. The only differences between the other Game Boy videos and this one as well is the way that the whole sort of program is organized. So I have, if you've not seen the others or you are not interested in the master system at all, there are key things in these other videos, as they all use GBDK. Lots of the code is very similar amongst them. So this here indicates the game state. This is a constant which holds which state the game is in, although I call it main state here. This is the main game state. At the start of the game here, we're purely interested in setting up the graphics, which will be there for the whole of the game, initializing the sprite data for the whole of the game as the sprites don't change. We then copy across the tiles for, in fact, wait there a minute, one thing I remember now, yeah, I forgot to add this in, so I'll put that in for yourself. I'll need to update that in the PlantBlitz game. I forgot to do that. It's important to make sure that the title screen is cleared each time. It looks fine the first time round, as in the start here we clear the screen when we set everything up. So how things go is you set up the main routine first, then you set the main state, and then the game is always in one of these states constantly. Mainly it'll either be in the run parts of the title screen or the game. This makes it easy to break up a game into just segments or components, whatever you want to kind of call them. We always have an initialize function for each and a run function, and then anything else inside of here is local to that module. So that's all I want to cover here. Let me know if you've got any more sort of questions, or you think I should have gone into some more detail. Another thought I've been having recently as well is possibly creating a desktop version of some of these programs, which you might find useful or interesting to dive into. Let me know if you'd like me to create some desktop versions of these. I can always create a virtual console of the Game Boy in SDL, which will run on the desktop. So yeah, let me know any sort of ideas that you might have with that, or thoughts that you have for that. If you'd be interested in a virtual console version in SDL, then just let me know in the comments below. Right, that's it for this video. Thanks for watching.